Ciao! Here is a conversation with Michael Betancourt. Dr. Betancourt is an experimental physicist and applied statistician focusing on broad-scale applicability of Bayesian reasoning in science. He works as an independent consultant and is known as one of the core developers of STAN, a probabilistic programming language for statistical inference. We start talking about his physics background and his passion for Bayesian reasoning. We then talk about the challenges and opportunities of conducting research outside academia, from the necessity of alternative means of funding to the intellectual freedom gained outside institutions, being able to make everything freely accessible, for example. We then introduce Bayesian reasoning and the potential of the STAN language in a number of scientific fields. We go inside what STAN does, talking about Markov Chain Monte Carlo, and focusing in particular on Hamiltonian Monte Carlo and on the good properties of symplectic geometry. We talk about the relations with convexification methods and the limitations of the use of Hilbert space methods and machine learning techniques. We close briefly touching on the Poincaré recurrence theorem, Hamiltonian chaos, and geometric ergodicity. I hope you enjoy it. To support this project, please subscribe to my YouTube channel, connect with me on Twitter and LinkedIn, and support me on Patreon with a monthly membership, following the links in the description. Okay, then thank you again for joining. I would say the first question could be about your background. I'm interested in how the open questions you're facing now in your research emerged, and so where you came from and what's the open things you're seeing now.
So my story begins a long time ago. As a physics student, I was doing experimental physics, particularly experimental particle physics. Mm-hmm. And, I kind of how I always thought my life was going to go was just trying to measure things and run these big experiments. And when I got into grad school, I was kind of given this analysis, and one of the postdocs kind of just sat there and said, hey, this is supposed to be a hard analysis. You should use some machine learning on it. I had taken stats classes in undergrad. I had taken analysis classes. I had done a lot of research. But I hadn't heard too much about the machine learning stuff. So I went to a friend of mine who had had the fortune to go to Dave Mackay's classes in Cambridge. He did a semester abroad, and he had done neuroscience and a little bit of computer science. So he had kind of a more accurate or up-to-date range of what was going on in the research side of things. And so he ended up recommending two books, which were very influential in my early life. Which was Dave Mackay's Information Theory, Inference, and Machine Learning, and then Chris Bishop's Pattern Recognition, Machine Learning. And those were particularly influential because they're, in a large sense, kind of secret Bayesian books. Chris Bishop's book in particular takes a lot of machine learning methods and shows how they can be written as these probabilistic models. And then the outcomes of the models are just the standard Bayesian inference over those models. And that got me really excited to think about, and that really clicked because in the science side of things, you're building these experiments and you know what the models are. You know how the data is generated, the underlying physics, or at least you have approximate models for that stuff, all the way through the end of the detection mechanism. And that knowledge is not really manifest in most statistics. You take a statistics class and it says you run this method of moments estimator or this maximum likelihood estimator, and there's not really a strong sense of how there's no connection to that experimental knowledge. And in the machine learning side of things, it's the same. It's just, here's this algorithm, it's black box, run it, don't ask any questions. So Bishop's opening things up a little bit and showing how there are these models here. And Mackay has this one chapter where he talks about this meeting he had with Steve Gohl, who got him started on the Bayesian side of things, the Bayesian path in life, if you will. And that started off with kind of you have this broken detector, it's truncated in its outputs. How do you model it? The standard estimators don't work, but you can just write down a model, throw it into Bayes' theorem, and you get your Bayesian inference out. Now, unfortunately, the book doesn't kind of go much more beyond that, but that was enough to get me really excited. And then I started doing as much research as I could into modeling and Bayesian inference and implementation of Bayesian inference. And, I spent a long time on that. Most of that time looking back was not the most productive. Everyone learns when you first start, but without the right kind of mathematical background, It's very easy to just be misled into what's working, what's not working. It's very easy to put something together and get a numerical output in an algorithm. It's much, much harder to understand what algorithm you want to run, what output you should be getting, how an algorithm's output approximates the output that you're actually interested in. Those are much more subtle questions. And a lot of my early work, which I think is common to a lot of people, was pretty fragile in that respect. So fortunately, I had the opportunity after grad school to go to University College London first, and then University of Warwick eventually, where I was working on this Hamiltonian Monte Carlo algorithm, but it really was just kind of a second PhD almost of just learning the math behind statistics and probability theory proper, while working on a whole bunch of other things. And so I think the common thread to provide a very long answer to your question, the common thread is trying to model science, experiments, measurements, and what is the technology for building those models and then working with those models. And how do we actually connect the science side of things where people know the experiment, they understand how the measurement was run, but they don't necessarily have the greatest statistics background, and then taking a lot of the advanced statistical ideas and identifying those that are actually compatible with those experiments and can be adapted to those experiments, and so that we get this nice intersection where we're doing good statistics and good science at the same time. Unfortunately, I think it's a very sparsely populated intersection at the moment, and that's really what all of my work is driving towards right now, is trying to make it easier for scientists to do better statistics.
Right. And you're still working in the UK now?
No. I'm in America at the moment. After my postdoc, I kind of flirted around with academic positions. Nothing really worked out, and so I ended up coming back to New York. And so since then, I've largely been an independent researcher, consultant, kind of making my way through, surrounding myself with independent projects and things like that.
Right. Can I ask you a bit more about this? Because I'm interested in this independent way of working. I saw, for example, you have a Patreon page with a lot of supporters. So congrats with that. It's a fascinating way of working to me, because I mean, I have friends which are musicians, artists, let's say in general, and I feel researchers are more similar to them than usually it's thought.
I think I started off with a sour taste in academia pretty early, after kind of transitioning from physics to stats and then trying to get stats jobs, but it was never really, I wasn't the right path for a statistics job, and nothing, again, really worked out. And one of the challenges is once you get to the point where you're a more senior researcher and you have to start funding yourself, you need to apply to these grants, and you need to, it's not this, I think people often think of academia as you get the professor job and then you're paid to do research and teach. You're really paid to get your own money, and then you can do research and teach and things like that. So it's a tough system, and it is already a system where you are fundraising. But that fundraising goes through this grant system, and you have to sell things in a certain way. And I think there's a lot of unfortunate consequences of trying to cater to the grant calls and people following trends and following hype. And a lot of work in academia is really, really good, but it doesn't get presented well because people are presenting it as a way of selling it to these grant agencies and make it sound more hyped than it actually is. And what gets lost in translation is where that result might be appropriate and where it's useful. So I got frustrated with that pretty early on. Again, part of it, to be completely honest, I just didn't get academic jobs. So in addition to not being able to get academic funding, I had no success getting academic jobs. I applied many places, nothing really worked out. And so I didn't really have an option. It was, if I wanted to keep working on this stuff, I'd have to find a way of supporting myself. Now, what made all of this possible was that for a long time, I've been involved in an open source project called STAN. It's a software toolkit to facilitate Bayesian modeling and Bayesian inference. And through that community, I've already been doing a lot of consulting and teaching. So people are interested in using a tool like STAN. They might have hired me back when I was a postdoc or independent or what's it, like permanent researcher type position. And I'd go out, teach a course, help somebody out with the model, but that was always kind of a side gig. And I got to a point where I wanted to have the freedom to work on what I thought was the most prominent research. And so I made the jump to do that full time. So I'd already had a head start in kind of accruing a network of potential clients and potential attendees for courses. I had a small but reasonable following on Twitter, and that is where it all started. And since then, it's just been constant hustling of trying to build that community, identify the people who are really trying to do better science, both in industry and in academia, and help provide them the tools. So it's kind of this two-step process of finding the right audience and then providing the services to that audience. I do have a Patreon. One of the things I really hope to do is have most of my work public. And, so a lot of consulting projects are never going to be public. A lot of kind of private work is never going to be public. But I do have a lot of writing that I do going towards at this point, a rather large book that tries to take people from basic understanding of calculus to probability theory, probabilistic modeling, Bayesian inference, and kind of filling a lot of gaps that I think there are in the existing literature. So that is something I've always wanted to be public. And that is what the Patreon largely supports. Right. And, big shout out to everyone who's supported me in the past, currently supported me on Patreon. It's kind of amazing. It's gotten to the point that it is. It's a huge kind of honor to have that support. It's, not full-time support. It's not like I get paid my full salary on the Patreon. I still consult, I still teach. True. But it's if anything, it's almost more for the kind of validation and just the feeling of support that people are there. And it's a great community. Every time I put something out, I do a live stream. It's nice getting the questions and the feedback and just really great discussion. So, yeah, I think it's just all about, it's this weird little niche where there are not a lot of people. There's a lot of people who are interested in statistics consulting, but there's not a lot of people that are interested in being really careful in building models and really understanding that what their models are and the consequences of those models, and then extracting accurate inferences from those models. That kind of more careful work that I get really excited about is much rarer. And so again, it's all about finding that intersection, that niche, where I have a service I can provide and clients want that service. And I've been very, very lucky that although that niche is really small, I've been able to cater to that niche, to find that niche reasonably well. And who knows how long it'll all last. But for the moment, it's doing okay.
Right. I mean, at least, maybe I'm not a patron yet. I'm going to be soon. But it's a big inspiration. To see someone surf the wave of the moment, let's say, of the ideas without a structure around him. Maybe I should add that I left academia. I was doing a PhD. I left academia as well. So maybe that's why I resonate a lot with what you're saying. So yeah, no, definitely brilliant. And the book you said is in progress.
Yeah, so I often talk about these case studies that I write, which are really just chapter drafts. And they're all up on my website, and I've started to organize it so you can start seeing what the kind of book structure organization looks like. I have a few more to do, and then I at least have rough drafts of everything, and then much work to go in and clean those drafts up. But again, it's meant
date for the publication.
No, especially with the pandemic, things have been a little chaotic. There's every time I write a new one, I want to go change another one. Right. So it's this challenge of a really good book should be coherent and concise in the right ways, but expand on all the little details in the right ways. And there's so much folklore in statistics and just this knowledge that gets propagated, not in books, not in papers, not in literature, but just, at conferences or from research mentor to a research mentee. And a lot of it is in my opinion, kind of garbage, but some of it is really important. And trying to organize all of that together in a clean way is a challenge. So that's an ongoing project. And again, the support of the Patreon is great. I do want to note that, for anyone listening, the support on Patreon is amazing, and I really appreciate it, but it's by no means necessary. And all of the work I do goes public, a month after it goes on Patreon. So there's really nothing you're missing out on if you're not able to support. That's something that's really important to me. But, if one does want to support, I'm not going to say no.
Sure. Great. Yeah, no, I mean, let me touch again on the inspiration point, because I mean, this position gives you so much intellectual freedom, I think, that one thing is that you're able to say, this is garbage, to do criticism without feeling like you're, I don't know, gonna pay for that in a grant application or something, compromises, things like that. And the second thing I think even more important is that you have on your website impactful research projects, which I think is a brilliant thing. I mean, I'm always scared. I have a document for my ideas, for the things I'd like to do, open question I see. And I'm scared to publish them because I feel, okay, people are gonna see this, they're gonna work on this, maybe they'll be quicker than me, and then I'm not gonna get recognition, and I'm not gonna get money. And so I don't know if it's Patreon, or it's just a mindset in which you say, okay, sharing it is more important than the money. So I share it. So how I'd like to arrive to a point in which I'm sharing my open questions as well. So how can I do it?
So I think for me, the big thing is that I don't want to do any of that research. I don't want to do a lot of the research I do, to be totally honest. As I mentioned before, my training is in experimental physics. I like running experiments. I love building experiments. I haven't been able to do that in forever. I like analyzing experiments. That's the thing that excites me, is working with a scientist, not just taking someone's data and trying to analyze it, but working with the scientist, understanding where the data came from, all the nuances in the data, all the little things that we have to model. That is the stuff that really keeps me going. Mm-hmm. And a lot of the more theoretical work I do is not something I'm super passionate about. It's stuff that just no one else was doing. And it's, and I've had to learn a lot of math, a lot of differential geometry, a lot of probability theory, a lot of statistics. And in hindsight, yeah, it's been really rewarding. And I have enjoyed a lot of it, but it's not what I'm passionate about. It's something I've kind of had to do to support that scientific analysis. So a lot of the stuff I put up on that, interesting projects page I think it's a little out of date. Some of those have actually had some progress on them. Mm-hmm. At some point I should go update it. Who has the time these days? But in some sense, it's kind of like, I would love other people to solve those problems. I'm not interested in the credit. I'm not interested in who does it. I just want the result to be done. And I don't have the time to do a lot of that stuff. And in some sense, I don't have the training to do a lot of that stuff. Okay. So I put a lot of stuff out there. It's just, on one hand, I do get people reaching out saying like, hey, I'm working on this project. What should I do? Or I'm working on this project that my advisor said to do, and I have to be like, I don't think that's a great idea. And having some, alternative is always helpful. So part of it was motivated by that. Another part of it was just like, here are the problems I wish we could understand so that I could focus more time on doing science and, getting that stuff out. And, we both talked about leaving academia. It's been a hard process of kind of deprogramming myself from that kind of academic validation mindset where, your whole self-worth is driven by, firstly your grades, and then the research projects you get, and then the grad school you get into, and then the papers you might get, or the qual scores you have, there's always some kind of external validation. And it gets to the point where that external validation, or that dependence on that external validation, gets exploited. And you start getting, people going into these not great positions, but feeling privileged to have them. And that then leads to the academic system as a whole really taking advantage of people and abusing them, in my opinion, not great ways. But, as much as I've gone at it, I was lucky to get out of that system and find a niche for myself. It's still hard to you still kind of long for that validation a bit. but the one step I have been able to make is not necessarily needing the, if I put a paper out, it's not for me. It's for the audience. If I put a piece of writing out, it's not for me. It's for, a community or a particular audience that looks at what I do. And I think that's been the one thing that has helped me find a kind of a more healthy perspective, is that my independent research, my consulting, my teaching, it's all for an audience. It's all for a purpose. It's not just because I want to get accolades. It's not just because I think it's a fun little result. It serves a purpose. And, you had mentioned earlier that, I have this freedom to critique and complain about things. And sure, I do, but that wouldn't necessarily go anywhere unless there was this purpose with it as well. And I think that's one thing that has sustained this little niche that I'm in, and that I've been relatively sincere as I can be, although we're all, flawed humans, but sincere as I can be in saying, here's my goal. I want to improve probabilistic modeling and what we might call generative modeling, and an accurate inference on that. And I try to make that very clear. And then I try to put stuff out there so that anybody who's struggling and they don't know those terms, they don't know why they're struggling, but they're trying to develop better analyses, and they're seeing the problems with a lot of the conventional statistical methodology in their fields. They can see someone complaining, and then they can go to them and convene and have some sympathy there, but also they get tools on how to potentially do better. And that's the main thing. It's not just, it's one thing to build a community where people can no longer feel alone with the struggles they've had. They can find people who are thinking like them and have struggled with the same kind of issues. But I think even better is once everyone gets together, they now have a path forwards to progress in their particular fields. And that's what I'm striving to do. And I think because everything I do is centered around that, it's not about me anymore. It's about that progression and about putting those tools together. And that there's a huge freedom in that, and not needing the validation, not needing just so long as that progression is being made.
Right. I will need a month just to think about this, but yes. Yeah, maybe can we start? I mean, this is I wanted to talk about these things which are not technical, because they're how do you say, cutting close to the bone. But yeah, let's have fun. Can we please start by discussing what STAN is, what your role was in the development of that, and who is the target audience for such toolbox?
Right. So STAN it's not just a program. It's actually a collection of libraries that enables a few different things, but it's all about
written in C++,
Bayesian,
right?
The main library is in C++. And then we have interfaces that expose those C++ libraries into things like Python, R, the command line, etc.
Okay.
So it's meant to be a tool that really facilitates Bayesian modeling and inference, no matter what kind of computer setup you might have. Whatever your analysis environment is, the tools will be available to you. And there's kind of two main features, in my opinion, on kind of the structure of STAN. One is a probabilistic programming language. So this is a computer language designed for building probabilistic models, in particular Bayesian models. So these are models of how a measurement proceeds, how observations are generated. And then once you've constructed that model with your STAN program, we have inference engines, inference algorithms that will take that program, condition it or evaluate it on observed data, and then identify the configurations of that program, the behaviors of that program that are consistent with the observed data. So to step back, kind of a one-line description of Bayesian inference, which is what STAN's trying to implement, is you build a model, and your model has all of these stories of how data could be generated. And some of those stories might have scientific interpretations. Some of those stories might tell you, if you kind of understand which stories generated the data, you have a sense of how to intervene, how to respond, et cetera. Very, very general idea. So our model doesn't tell us what stories are correct. It just gives a sense of what stories are reasonable. Then we go look at observed data. And what Bayesian inference allows us to do is identify which of those stories are compatible with the observed data. So now we're getting a filtering mechanism, a selection mechanism to identify the compatible stories. Now that conceptually and kind of theoretically, that process of filtering out is quite straightforward. It's just an application of Bayes' theorem, where hence the name Bayesian inference. But the mechanistic implementation of that is much harder. What we get is a prior distribution quantifies the stories that we think are reasonable before we look at the data. We get a posterior distribution that probabilistically quantifies the stories that are compatible with the observed data and our domain expertise after the fact. And we have to be able to quantify that posterior distribution in some meaningful way. So STAN provides a probabilistic programming language for building that model. And then it provides algorithms that can quantify the resulting posteriors for you. So you don't have to worry about that as much as possible. It can't be perfectly abstracted away, but we try to do a lot of the work for you. So as a user, you can focus your time on building the model for your experiment, your measurement, your analysis. Use your domain expertise to build that model bespoke. Don't rely on a black box model. Don't rely on some pre-built thing that someone tells you to use. Build the thing appropriate for your analysis. And then you plug it into STAN, and STAN will attempt to quantify the configurations of that model that are compatible with your observed data, so that you can then report that in a paper. You can use that to inform decisions. You can do all kinds of things with the outcomes of those inferences. So STAN is that twofold step of specifying the model and then fitting that model, of quantifying the stories, the configurations of that model that are compatible with the observed data.
Right. And the complicated part is the identification of the best model, let's say, to estimate the posterior.
Right. So yeah, that's where there's just a huge amount of mathematical subtlety and challenge to have a tool that can take an arbitrary posterior distribution and quantify it accurately. And this is where I think there's a lot of, say, optimistic expectations in the world, where a lot of people take a statistics class and they do a Bayesian inference module. And it's often presented that constructing this posterior or quantifying this posterior is trivial. And so they should assume you plug it into some algorithm and some output comes out and they can trust that output. And that is an unfortunately misleading expectation, because it's just really hard to quantify these posteriors accurately, especially as you build more and more complex models. And so the tool that was originally put into STAN, something called Hamiltonian Monte Carlo. The reason I was involved in STAN is that in grad school, I was working on Hamiltonian Monte Carlo myself independently. Again, I was in physics and HMC. It's very physicsy. It looks like a physics simulation. And so it was something that was just immediately appealing. I started working on it and put out a few papers. And that is some of those papers, some of the STAN developers had seen early on. And this was when there was 2 or 3, maybe 4 STAN developers. So when I joined, it was a very small team. And since has exploded to a much larger team, a huge community, a lot of very exciting work being done with the tools. But one of the big things, and this is my opinion, not everyone agrees with this, but the huge things that we need in a tool like this is having those accurate algorithms. And that is something that Hamiltonian Monte Carlo is very uniquely suited to do. It's very robust. When it works very, very fast compared to most competing algorithms. It works on a much larger class of problems than other algorithms, especially older algorithms. And what's perhaps most exciting about it is when it fails in a very informative way, where you have some feedback, some diagnostic that it's not working, that it's not quantifying the posterior accurately. And then you can actually dig into that a little bit to get a sense of what's obstructing the accurate reconstruction. And so if you use STAN in a very careful way, you get this very robust analysis where you have some confidence that you're actually getting a faithful picture of what your posterior inferences are. Now, just like any tool, you can use it less carefully and you can ignore that feedback. You can ignore those diagnostics and just get some answer. Maybe it's right, maybe it's wrong. But at least there's that opportunity there. And that's the part of STAN that I really push and get excited for.
Right. And can you explain to people that know it what are the principles guiding Hamiltonian Monte Carlo, and maybe before that, Markov Chain Monte Carlo in general?
Yeah. So in a conceptual picture, Markov Chain Monte Carlo is all about running these Markov chains, these sequences of states that are kind of conditionally built from each other. And you want to design this transition, this jumping rule that tells you how to go from one state to the next in a way that it converges towards the important neighborhoods of a given distribution. So you give it a probability distribution, the Markov chain hopefully converges to the important regions of that distribution and then starts exploring those important regions. And the idea is that it's trying to, if you look at kind of the history of the Markov chain, the history of those states, if it's actually converged, and those states give you this kind of quadrature grid, this kind of discretized exploration of your distribution, and then you can use that to characterize properties of the distribution numerically. You can characterize moments and other expectation values. That's the more technical side of it. And so the goal of an effective Markov chain Monte Carlo algorithm is something that can very quickly explore the space, explore your parameter space, your configuration space, get to those important regions, and then explore all of those important regions. Hamiltonian Monte Carlo is an implementation. It's a particular Markov chain Monte Carlo algorithm, and it uses Hamiltonian dynamics for those update rules. So it's still an MCMC algorithm. You still have a sequence of states that get updated. The next state gets updated based on just the previous state. But how those states are updated is really important. And what Hamiltonian Monte Carlo does is it basically emulates a physical system and then runs the physical evolution of that system. Mathematically, what it's doing is it's using gradient information. It's taking gradients of your model, and it turns out you can't just follow the gradients of the model because that will take you to the mode, and that's not where the important regions are. Right? We're not trying to optimize here. We're not trying to find one point. We're trying to find all of the neighborhoods that matter. So following the gradient naively wouldn't give us something very helpful. So what this simulation of physical system does is it kind of warps the gradient, it twists the gradient in just the right way so that if you follow those dynamics, you end up staying in these regions of high probability, these important regions. So what the dynamics actually allow us to do in some sense is if we have one point in a good region and we run these dynamics and follow these transform gradients, we'll end up at a new point that's also in a region of high probability. If we start off outside of those regions and run the dynamics with very high probability, we'll tend to fall in to those regions. So you can kind of think about it like a bowl. If you put a marble in a bowl, right? The marble's, if it starts off very high on the bowl, on the edge, it's going to fall down really quickly and go to the center. But it doesn't actually spend that much time in the center. If you actually look at how often that marble is at the center, it's very, very small, because when it's at the center, it has high kinetic energy, has lots of velocity, and it very quickly leaves. And then it goes back up to the other edge. And so if you look at the trace, if you kind of follow a trajectory of a marble in a bowl from up top, you'll see that it kind of eventually over time, it fills in this donut, this kind of annulus around the center. And that's very similar to what a important region of a probability distribution is. It's not the center that matters, it's the area around the center. And so you can kind of see how those dynamics are already well suited for this probabilistic exploration. So again, there's a lot of math that goes into that, and these descriptions about physical systems and following transform gradients are all very vague. And it's just, unfortunately, to get precisely what's going on, you have to go dig into a lot of technical detail. But that's roughly the idea of what's going on, is we have a way of constructing these fake physical systems, running the dynamics of those systems, and when they're constructed in just the right way, they allow us to move from one point in a region of high probability to another point in a region of high probability. One story consistent with the data to another story consistent with the data. And if we keep running this Markov chain, hopefully we're able to find most of the stories consistent with the data.
Right. Okay. And the fact, so let me give a bit of context for this point for my audience and also for myself, because I'm coming to these topics from, let's say, uncertainty propagation in dynamical systems. So you have, for example, you have techniques in which you define a you use a Galerkin method in which you project your PDF onto orthogonal directions with respect to some inner product. And to do that, you needed to compute an expectation of basically the propagated set of states to the next step. And yeah, so one could use simple trivial quadrature rules to compute the integral to have the expectation, but also one could use some MCMC. And so to specify this, I wanted to say that basically when you talk about Hamiltonian trajectories, dynamics, you're not referring to a dynamical system. You're referring to the process of approximating, to exploring this landscape, right? I mean, we're not dealing necessarily with dynamical systems.
So what actually happens behind the scenes is a Hamiltonian dynamical system is constructed. So there is a full dynamical system.
Which is not the same as the one what is seeing when doing uncertainty propagation, for example.
Yes.
Okay.
So this is you have a target distribution, a probability distribution that you're interested in quantifying. And you want to run a Markov chain that has the sequence of states that converges to the important regions of the ambient space that have high probability for that target distribution. Hamiltonian Monte Carlo is just the way we update those states. So there's no kind of global dynamical system. It's just going to be these local dynamical systems. And what ends up happening is when you're at one of those points, we basically lift to a higher dimensional space by adding momenta. And you add momenta in just the right way that there's basically this emulated physical system. There's it's a geometric Hamiltonian system. There's a symplectic form. There's a Hamiltonian function. You can run Hamiltonian dynamics, and then that gives you because of how that system is constructed, those Hamiltonian dynamics stay in regions of high probability. So you're kind of engineering the dynamics to be compatible with your probability distribution, that distribution that you're trying to explore. And so this gets a little bit confusing because you can have a dynamical system that forms your probabilistic model. So your target distribution could be a probability over a dynamical system. Hamiltonian Monte Carlo is going to add more dynamics on top of that. So it gets a little bit, complicated in how it all goes. And so if you want to think about it abstracted, HMC is just the way we update those states. But if you look under the hood, in that update, there is a full Hamiltonian dynamical system that's used to evolve that state forwards. And that Hamiltonian system is engineered in just the right way so that the original target distribution is preserved under those dynamics.
Mm-hmm. And the idea it's Hamiltonian because a lot of ideas from Hamiltonian mechanics are used in the implementation of this.
Well, it's using actual Hamiltonian dynamics. Okay. So you start at your point. You can think about the target distribution as defining a potential energy. Mm-hmm. And then when you add momenta, you introduce a kinetic energy, and that gives you a full Hamiltonian system. Right. You can evolve that Hamiltonian system forward. That evolution will require, if you look at Hamilton's vector field, you'll get a gradient of your target model, which the gradient of the potential, the force term, that's where the gradient comes in. And then there's other terms depending on the gradients of the kinetic energy. But that's just an ODE that you solve. When you throw a symplectic integrator on it, you numerically approximate those dynamics, and that gives you your update.
Right.
But it is a complete Hamiltonian system, hence the name.
And of course, someone using Stan doesn't have to do a course in Hamiltonian mechanics to use it.
Yes.
Everything is
that's the huge benefit of Stan, is that you don't have to understand how this is happening. You don't have to know how these states, these Markov chain states evolve from one to the next. You just put in your model, you hit go, and Stan automatically gets the gradients. You don't even know how to differentiate your model. Stan uses automatic differentiation for that. Runs everything, gets the gradients, generates the Hamiltonian trajectories, and then all you see are these output states. Or if you're just looking at the summaries, you just see the expectation values of these, the estimators of certain expectation values. Now, the only challenge is that if these Hamiltonian transitions aren't as effective as you might hope, if they're not actually giving you a full picture of your target distribution, if there are some regions that it can't explore, there's some kind of barrier that prevents you from seeing everything, then you have to get these diagnostic output. You have to validate that your computation's working. Mm-hmm. That is a little bit trickier because ideally, yeah, you would know all of the details of HMC, you know why those diagnostics are failing the way they are, and you can understand them and you can follow up and investigate why they're failing as best as possible. But there is a nice intermediate level where you can build up some conceptual understanding of what the diagnostics mean without understanding the full depth of dynamical systems, and then use that to investigate what's going on. And again, that's a lot of my teaching, a lot of my consulting is just that process. We don't get into anything about how HMC works. We're just looking at the diagnostics and investigating them to understand why a fit is failing. So we abstract it as much as possible, and if everything works, you can ignore all of that detail. Mm-hmm. But when things fail, you got to go a little bit deeper to understand what's going on.
Right. And can we talk about a bit, I would say, research questions? I have a colleague that worked on convexification methods for optimal control, so for optimality. Would some technique like that play a role here, in the sense that you have still a landscape? You said you're not looking for a minimum, you're just exploring, but maybe can you map this weird landscape with, I don't know, a lot highly non-convex, and use some convexification method to deal with the problem here?
So I think, and you can correct me if I'm kind of misinterpreting the term, but a lot of convexitization methods, I just interpret them as second order Taylor expansions, right? You're just looking at the local structure of your model and you're using that local structure to update where you're going. And if you keep that second order approximation, you get a little convex neighborhood and you can optimally move within that neighborhood.
Okay. I mean, to be honest, I'm not sure about I don't think that's the meaning of convexification. So I think this is related to basically linearization in dynamical systems, which is something I'm looking into right now. And you can, linearize in the sense of Taylor expansion around a point, around a fixed point. You have a phase-space diagram around an equilibrium. But there are some ideas coming from functional analysis, Hilbert spaces, in which basically you're mapping your state space to a higher dimension, infinite dimensional space, in which everything is nice, is linear, is convex. I think convexification methods are similar in the sense that you're not doing a linear approximation, a local linear approximation. You're trying to get a linear operator that matches the overall shape of this non-linear, non-convex object.
Yeah, so I think the challenge is, so let's start with the local approximation, right? So just, you do this local quadratic approximation, this local linearization. If you kind of think about that as defining a local convex system, you can optimally solve that. And, in some sense, any kind of gradient descent method, any kind of local update method, it can be framed in that form. The problem with those methods is that they require you to move within that domain of validity of that approximation, right? You can't go past that domain because otherwise the linearity breaks down or the convexity assumption breaks down. And so there's a certain kind of built-in speed limit where you can make these small little steps, and those steps will be optimal, but they'll be small. And the second you try to make bigger steps, you start running into problems. And the more non-convex your target is, whether it's an objective function or a target distribution, the smaller of a neighborhood you'll get where you're able to make moves. And this is a general problem with a lot of computational methods, that if you're using local information to adapt your algorithm, that adaptation is only ever going to be valid in that local neighborhood. And if you move too fast, if you move too far, that approximation breaks down. So there's this interplay between adapting as fast as you can and then moving as fast as you can. And if you move faster than the adaptation, you end up, going off course.
Right.
And if the adaptation is kind of fixed in its speed, then that serves as your speed limit, and you end up going, just fast enough where the adaptation is able to catch up. One of the beautiful things about Hamiltonian Monte Carlo is that while you can think about there being certain kind of local approximations to how the steps are being made, there are some global symmetries that are built in that ensure that those local approximations get chained together really well. And that's how Hamiltonian Monte Carlo is able to achieve such fantastic performance. So it can make these huge jumps in space as a kind of product of these little numerical updates. But those numerical updates are being driven by this global system, this global symmetry that ensures they chain together, they compose together really, really well. So you can go really fast without verging off course. And that's what makes the Hamiltonian side of things so special. And even then, if you try to tune HMC, if you try to adapt it to local structure, you run into the same problem. HMC goes too fast. It just zooms, and your local adaptations can never keep up.
Right.
Hilbert space methods and some of these kind of infinite dimensional lifting methods, let's say, there is a lot of simplification that you get in terms of it's not to be convexity. What's the word I'm thinking of? There's another one of these properties that is in some sense kind of trivial to achieve in a Hilbert space because there's so much room that everything is kind of far apart. You have all of this space, and then you get convexity and other kind of properties or kind of hold with probability 1. But there's still going to be a few limitations there. One is that you have to construct this system. You have to construct this infinite dimensional system that you lift into. And there's going to be lots of ways of doing that. And then the second part of that is, yes, you might be able to move very efficiently in that higher dimensional space, but that doesn't mean that the projection of that motion is actually all that far. Right. So if, one of the kind of subtleties here is if you're judging things based on, this is convex, so I can make these huge jumps because it's globally convex. I can make these optimal updates within a few steps. That's all great. But a lot of that motion is often confined to those new dimensions that you introduced.
Yes.
And if you actually project things back down, especially when you have an infinite number of new dimensions, that the bulk of any motion is going to be in those infinite dimensions and not necessarily in those finite dimensions that you started with.
Right.
So yeah, you can do that. You can lift to the higher dimensions. You can try to generate some motion there. But when you project back down, you end up having not moved very far.
Yeah.
Right. All of your motion has been in this transverse direction, these new dimensions that you introduced.
Yeah.
And so what ends up happening in a lot of these techniques
is wasted, let's say.
Yeah. Well, or it's wasted, or it depends very sensitively on the choice of that lifting map. It depends on that Hilbert space you embed into. And so what you end up getting is this very fragile tuning problem. There are some configurations of the method that might work okay, that might in fact work really good, but there's going to be a lot that work really, really poorly. And the problem is that the maps that work well, the tuning of your method that works really well is going to change from problem to problem. So there's no global configuration that you can put into a package and have people use. People are going to have to tune that for themselves separately. And somebody who has access to a huge supercomputer or this huge cluster of cloud resources, you can try 100 different configurations and see what works, grab the one that works for them. That could be useful. But for most people, they're not going to have that luxury. They're going to have to set one or two settings. And I think what differentiates a good algorithm from a bad algorithm is if you have a sense of how to tune the method. If you have a sense of what are the consequences of the degrees of freedom in your method, how those degrees of freedom interact with a given target, objective function, distribution, et cetera, and then using that interaction to build up principal tuning mechanisms. This is another huge benefit of HMC. We can use that geometric dynamical system structure to understand what happens when we change the step size of our symplectic integrator, what happens when we change the kinetic energy. Now, the analyses aren't perfect, but we can build up quite a bit of intuition with that. And that's, Stan is built on all of that. Stan automatically adapts to get good performance for a given problem. And the adaptation outcome is different for every single program that gets run because it's adapting to that bespoke problem. And if we didn't do that, terrible performance. HMC is better than other algorithms, but we still wouldn't be getting good enough performance to really scale Bayesian inference to the places that we've been able to. And so this is something I always look at whenever I see a new method and somebody, is kind of claiming that it's working really well. I'm always going to look for under what circumstances did it work well? Did they break it? Are there other circumstances where it's not working well? And how fragile is the configuration of that algorithm? How well can you tune it without just brute force running it over and over again? So I can't speak to the particular details of the methods that you're referring to, but in general, that's the kind of pattern and trend that I tend to see is that, yeah, there might be a way of doing it, but what's missing is the principle of what tells you the right way of doing it. And I think that's what makes, not to harp on Hamiltonian Monte Carlo again and again and again, but it really is this kind of miracle because not only does it have the math, it's not just a dynamical system. It's a dynamical system that is kind of properly adapted to the probabilistic side of things and allows us to understand how to tune the method to a given problem. It's all of these kind of miracles layered on top of each other. And if any of those miracles didn't work, the method wouldn't be the power that it is.
Right. Yeah, and it seems, my understanding that basically you're building on 150 years of work on Hamiltonian mechanics to have this sound stone that you can use to hit everything.
Yeah, it's kind of miraculous where Hamiltonian Monte Carlo is and the maturity of the mathematics that had to go into it being what it is. I had the luxury of talking with Simon Duane a few years ago for one of my podcast episodes, which is, I believe they're both publicly available. If you go to my Patreon and search the podcast posts, they should be publicly available with or without an account. And he was he was the lead author on the original HMC paper, the original hybrid Monte Carlo analysis in the 80s. And, he tells the story of where it came from and a lot of the heuristics that they were putting together. And they didn't really understand the deep mathematics they were connecting. Brilliant people, all of them. But it was just a lot of like, okay, this kind of works this way, this kind of works this way. And they were able to put this thing together. And what's ended up happening over the past few decades is as we've been able to put more mathematics underneath this stuff and fill in why it works and why this physics method applies to any probabilistic system and understanding that intersection of probability theory and geometry and dynamical systems, putting in a richer theory, understanding, what are the role of Hamiltonian dynamics? Why Hamiltonian dynamics? Why this physics thing? Are there other dynamical systems that aren't physics related that would work? And the answer is yes and no. But there's something special about symplectic forms and symplectic geometry that really does a lot of work here. And just recently, I was working with a colleague, Alessandro Barp. We have one preprint out that kind of touches on some of the work, but hopefully there's another much longer paper coming. And really, Alessandro did most of this work is generalizing the geometry of these probabilistic dynamical systems, generalizing the mathematics of measure preserving dynamical systems. And if you start filling it all out and then ask, okay, so what is the intersection of dynamics that are measure preserving, dynamics that are easy to or robust to simulate, that have a kind of backwards error analysis capability in them and the right kind of global symmetries. And then a few other properties that are kind of easy to correct and things like that. You're almost always led back to Hamiltonian Monte Carlo, to that original system that was set up in the 80s. And it's so exciting that the math that's being used is really just state-of-the-art contemporary differential geometry. It's geometry itself has evolved so quickly over the past 100 years. And it's the more contemporary perspectives on it that really illuminate the structure, the probabilistic structure of these dynamics and why they can be suited to these algorithms. And then you have, the modern tooling of things like automatic differentiation that allow us to implement the method automatically, and not even to mention the other stand-related things like the probabilistic programming languages. So it's this confluence of the kind of original confluence of heuristics that led to this method that has really sustained so long, and as far as I can tell, will sustain quite a bit longer. And then also the confluence of theoretical maturity in the probability theory, in the Markov Chain Monte Carlo theory, in the geometry, in the dynamical systems understanding, that, when you put all those things together, you start seeing why those heuristics were so special and why that is such a robust tool. So it's not just that a method happens to work. We actually have a real understanding of why it's the special combination of things that work. So what's kind of ironic is that these stories that we tell, the conceptual stories that, it's a physical system and you're following this, landscape, et cetera, all of that is unnecessary. All of that is completely coincidental. The real magic is this theory, this mathematical structure, which is super fun and exciting. It's just kind of unfortunate that no one ever wants to hear about it.
I mean, it looks, maybe because I'm interested in dynamical systems, this is the most interesting part for me. So if I can ask a bit, do you have some more time? Yeah. So I have two questions. One, I think you kind of already answered when we discussed about Hilbert spaces and the power of symplectic forms. I've seen a number of papers on, for example, neural network-based approach for phase space integration, neural importance sampling, or normalizing flows for computing, basically exploring a landscape in the broader sense. Your feeling is that symplectic forms are gonna stay? Yeah,
I'm not a huge fan of a lot of what's coming out of machine learning for statistics. And that's a very important caveat. For a lot of engineering tasks where uncertainty doesn't matter, it's fine, right? The classic example I like to use is if you're trying to come up with automated image caption, you don't need to come up with every possible image caption. You just need one that's good enough. And in a task like that, you don't need to explore every possibility. You don't need to explore the full configuration space. You just need to find one thing that works okay. And for those kinds of more engineering tasks, I think those methods work fine. But the second you start transitioning into more careful exploration, more complete exploration, and really trying to understand all of the configurations that are consistent with a given data set, a given training set, if you will, those methods become much more problematic. You can construct some neural network-based normalizing flow, and every configuration of the network is going to give you a different flow. It's going to give you a different map from your simple normal distribution to some complex distribution you're hoping approximates your posterior, for example. And every one of those different maps will give you a different approximate quantification of your posterior. And those approximations will have different consequences in the kind of inferences that you want to communicate, the decisions that you want to inform. There are none methods of that form, and that more machine learning perspective, in my opinion, that are even close to having faithful, complete characterization of a distribution. Again, they can give partial pictures, and if a partial picture is all you need, go for it. But if you really want to understand everything that's going on, you need to put the effort into really quantifying the full distribution and understanding when you've quantified the full distribution. And that's something that Hamiltonian Monte Carlo is just really, really good at. And so again, I just want to kind of demarcate that. Like a lot of those methods for engineering, great, awesome. But for statistical analysis, for inference, I think they're much less well suited. And unfortunately, I mentioned before that just a lot of papers get hyped up and they're presented in these ways to, if anything, to get more grant money to get more interest from people, and not really framed in what they can actually do and what they're actually useful for and what their potential dangers are. So a lot of people who are doing statistics read these papers and then apply them thinking they carry over. And that's where I get really frustrated. Mm-hmm. There's just a lot of, I remember when I was in grad school in physics, people were starting to play around with these machine learning ideas, but it was really statistics in a lot of science isn't very good. And the sophistication of the machine learning methods that were being played around with weren't very good. And now we're getting people throwing around, well, I'll use this normalizing flow, I'll use this neural net, et cetera, and throwing out more sophisticated methods and working with computer scientists, but there's still not that appreciation for really quantifying uncertainty in an accurate way. And so, yeah, you're getting something, but how do you know if you're getting a faithful picture of what your experiment's trying to tell you? For engineering tasks, great. For statistical inference, not so much. And I do think one important place where there's a little bit of overlap in the engineering tasks in this more statistical problem is when we start looking at things like ethical AI, quote unquote, or fair AI, or really understanding the fact that when you're engineering a solution, that engineered solution often works really well for one class of people, and it's often really dangerous and problematic for another class of people. And if you want to get into quantifying those consequences and really understanding all of the outcomes of a method and all of the ways that it can fail, in my opinion, you're invariably led closer and closer to a statistical analysis. And so I believe that you really can't do a careful ethical analysis where you understand the provenance of the data, the consequences of the assumptions that you're making, the consequences of the decisions that you're choosing between. All of that stuff requires a really careful understanding that one would need to build a probabilistic model and quantify your posture accurately anyways. So they're kind of hard to separate out, in my opinion. That's I'm sure a little bit more controversial and people can debate about that. But I think what is less debatable is if you say that you have this distribution and you want to be able to quantify it accurately, then a lot of these other tools just aren't going to be useful. And something like Hamiltonian Monte Carlo is likely to be your best bet. Not always going to be true, but almost surely is going to be true.
Right. I see. Yeah, you let me know. I have questions about the relations between statistical mechanics, adiabatic Monte Carlo, the implications of ergodic theory for Hamiltonian Monte Carlo. You stop me when you have to go.
Sure. So I do a few more. Let me comment on the ergodicity stuff, because I think it touches on a comment you had made a little bit earlier. In that discussion that we were having about the kind of maturity of mathematics and the confluence of things that allow us to understand HMC as well as we do. As much as we understand Hamiltonian Monte Carlo, there's a lot more we don't understand. And there's a lot of dynamical systems results that we haven't applied yet to the understanding of HMC. So when we talk about ergodicity of HMC, we're talking about ergodicity of the Markov chains that it generates. That's a very statistical picture of ergodicity. You have some kind of central limit theorem that kicks in for expectation value estimators, and you verify when that central limit theorem kicks in, and then how quickly it kicks in, and then the consequences once it's kicked in. That's the kind of important ergodicity. The dynamical systems ergodicity is related, but it's not quite appropriate to the MCMC side of things, because it's only relevant to that one update, right? The Hamiltonian dynamics only go for one update at a time, and then they get refreshed, they get changed a little bit. So you can kind of make the argument that if you have ergodicity of your Hamiltonian update, then your MCMC updates should be really good. But you don't need ergodicity, the dynamical ergodicity of your dynamical system of those Hamiltonian updates didn't necessarily get good MCMC updates. You can still get good MCMC even with, not the greatest dynamical ergodicity. So there hasn't been a huge focus on that, but I think there's a lot of interesting opportunities in understanding that to get a better sense of when we can optimize the method and when we can ensure better MCMC performance. So things like, Hamiltonian chaos, when do these Hamiltonian trajectories explore level sets, explore the microcanonical distribution really, really accurately? Empirically, it seems almost always. And there's some understanding of that, and that most of these statistical problems that we build aren't supersymmetric. You basically have to have a normal, an independent, identically distributed normal target to get the kind of symmetries you need for the CAM theories to hold, and for you to get these invariants and to not have any kind of chaotic system. But what are the further consequences of that Hamiltonian chaos? I'm not sure. There's a book by I'm going to forget the name. It's like Zalewski, a researcher at Courant. Yeah, it's like, it's all about Hamiltonian chaos. And as far as I can tell, he was like the only person who ever worked on Hamiltonian chaos. And there's just a lot of really interesting stuff in there about the kind of behaviors you get with these kind of local trappings and Cantori and all kinds of stuff. And I don't know if any of that applies to HMC. It might be happening behind the scenes and we just don't see it because we're not looking for it. And maybe it has consequences, maybe it doesn't, but there's just, that kind of analysis hasn't been done. I think perhaps the most relevant result is Poincaré recurrence. So right now in STAN, we use a dynamical HMC sampler where the integration time of our trajectories is chosen dynamically based on a geometric condition. That geometric condition is motivated by what was in the original Nuts paper, this no U-turn sampler. So STAN doesn't use the no U-turn sampler. We have a more advanced sampler at the moment. And the criterion has been generalized and adapted as well. But the original motivation is basically, if you kind of think about your level set as being spherical, as your trajectory expands, at some point, it's going to start moving back on itself. At some point, it's going to get to the other side of the level set and then start returning to where you started. And so it's using a Euclidean notion of distance to define that metric. And we generalized it to use more dynamical system stuff. And you're kind of looking at how the momentum starts changing against the integrated momentum. But really, I think the right way of thinking about that to determine how long you want to integrate is to define some kind of recurrent setup where you define some neighborhood around your initial point, you let your trajectory go, and then once you recur back into that neighborhood, that's when you stop. But how big of that should that neighborhood be? How do you determine when inclusion back into that neighborhood without relying on a metric and things like that? How is it I can make it like a purely dynamical system that just uses a symplectic geometry. That's something I've speculated about for a long time, and I think there could be some really interesting results come out. It's just an opportunity sitting there. If you know enough about the probabilistic side of things and the statistical side of things and the MCMC side of things and enough about the dynamical system side of things, there's an interesting overlap. A funny story, so I mentioned David Mackay, who was I guess, I don't know what his official title was. He was professor of engineering, I think, at Cambridge, but he did a lot of statistics. And he wrote that one of those very motivating, influential books I'd read early on. But he also has a brother. I can't remember his first name, but he's a dynamical systems professor at work. And when I was at work, trying to spread the gospel of Hamiltonian Monte Carlo. And look, to be honest, most people don't understand it. I can't sit here and say like, all right, well, if you knew symplectic geometry, here's how to explain it. If you knew this, here's how to explain it. Most people just aren't going to have those backgrounds. And so I have, come up with these pictures and these stories and these conceptual narratives. But I, can never, even with those conceptual narratives, you have to introduce a lot of stuff. But here's the professor of dynamical systems who studies, kind of ergodic systems and probability of dynamical systems and all of that. And so I sat down in 3 sentences, I was able to explain all of HMC. And he goes, yeah, cool. That makes sense. He's like, yeah, at holiday meals, Dave would talk about this HMC thing all the time. I never really got it. And I was just like, boom, boom, boom. And he goes, oh, okay, cool. That makes sense. And that was it. That was conversation was over. And so it just goes to speak to like a lot of the complexity of this method isn't so much the complexity of the method itself, it's the complexity of the background, right? And the tools that it uses. But the actual ideas behind the method are very, very concise and very, very elegant. And that's one of the reasons why I think it's so robust, right? Is that, compared to some other method where it's, it lacks the elegance of telling you what to do. It's just, here's the possible things you can do, but not what you should be doing. That leads to the tuning problems. But with HMC, we actually know what we should be doing. We have this elegant description of what's going on, provided you understand all of the background mathematics. And that's why we get the robustness there. So yes, so a ton of opportunities for bringing in other notions of dynamical ergodicity, dynamical properties, dynamical systems to better understand how to tune the Hamiltonian transitions and when they might fail and what kind of problems they might find in given problems. I do think there's a lot more to be done there and potential improvements on the methods that we're using.
Great. I think this is the best way to stop because it's the best place to start.